Now that I know about significant figures and what those mean, how do we use that to convey how accurate or how precise our measurements are? Well, first we need to talk about what accuracy and precision are. But it's important to know that for a measurement to be useful, you do need to know how accurate and how precise it is. Otherwise, it's just a number. You don't know if it's reliable. So we need to convey accuracy and precision. So what is accuracy? Accuracy is how close a measurement is to the true value or the accepted value. So this might be a textbook value that you get out of a textbook, or some other standard true known value. Precision, on the other hand, is how closely clustered together a set of measurements are to each other. So there's a small range of measurements. So looking at these four pictures, based off of those two definitions, try to think, is each picture, is it accurate? Is it precise? Is it both? Or is it neither? So pause the video, look at those definitions, and decide which ones are accurate and which ones are precise. Okay, so in here, this is maybe the easiest one to start with. This target is both accurate and precise. We've hit the bullseye. We're all here around the bullseye, and the shots are all clustered close together. On the other hand, this one is not accurate and it is not precise because the shots are not clustered around the bullseye and they're also spread far apart. This example is at least somewhat accurate. We seem to be going on all sides of the target, so at least we're not kind of consistently to one side. We're surrounding the target, but this is not precise because our measurements are all spread far apart. In this example, this is precise because our shots, our measurements are all very closely clustered together. But this is not accurate because we're not anywhere near the bullseye. Okay, so this picture kind of helps represent accuracy versus precision. So what does this mean in terms of measurement? How do you look at some measurements and decide whether they're accurate or precise or both? Well, let's look at this example. The true density of copper is 8.94 grams per milliliter. Two students each make 3 copper sample measurements. Student 1 has these three results, and student 2 has these 3 results. And I want to know which student is more accurate, and I want to know which student is more precise. So there are a couple of statistics we can look at to decide. We can look at the average. So if you average 7.3, 9.4, and 8.3, you will get an average of 8.3 grams per milliliter. And the range of measurements is the distance between the smallest reading and the largest reading, and that difference is 2.1 grams per milliliter. Let's contrast that with student number 2. If I average that student's 3 measurements, I get an average of 8.4 grams per milliliter. And the range is 0.8 grams per mil. Again, I'm just doing the largest value minus the smallest value. Based off of these calculations, who is closer to the true value? Whose average is closer to the true value? And that student is more accurate. 8.4 is closer to 8.94 than 8.3 is, so student 2 is more accurate. Student 2 is also more precise. their measurements are clustered more closely together. There's less range in the measurements. Therefore, student number 2 is also more precise than student number 1. So, now that we've kind of gotten an idea of how to look at accuracy and precision, we need to think about, how do we decide if we in an experiment did a good enough job with our accuracy? Are we accurate? Did we do a good job? And we can do that quantitatively by calculating percent error. So, percent error is a formula where you take the measured value that you got from an experiment, sometimes it's called the experimental value, minus the true value or the textbook value, divided by the true value times 100. Now, these are absolute value bars here. Absolute value symbol indicates that I should never have a negative percent error. Okay. So, percent error is comparing a measured value to a true or accepted value in order to calculate the accuracy of the measurement. A percent error of less than 10% is considered accurate. So that's our target value. If we're less than 10% error, then we're accurate. If we're more than 10% error, it's considered inaccurate. And as I said, that absolute value means you can never have a negative percent error. So let's look at a practice problem and see how this works. A student measures the mass and volume of a substance and calculates its density as 1.40 grams per milliliter. The accepted value of the density is 1.30 grams per milliliter. What's the percent error of the student's measurement? Well, the percent error is the measured value minus the true value divided by the true value. So the measured value is 1.40 minus the true value over the true value times 100. One thing that's tricky here, remember, we need to think about our significant figures. So when I do 1.40 minus 1.30, I'm going to get 0.10 as my answer. The calculator won't give you this extra 0, but you need to remember that it's there because we had 2 decimal places in each of the numbers in the problem, so we need to have 2 decimal places in that answer. I'm going to divide by 1.30 and I'm going to multiply by 100. Remember, this 100 is a constant. It does not affect our significant figures at all. Okay, so now I need to do step 2 of the problem. 0.10 divided by 1.3. When I do multiplication division, I have to think about the number of sig figs. So I've got 2 sig figs divided by 3 sig figs. So I'm going to need to have 2 sig figs in my final answer. 0.1 divided by 1.3 times 100. The calculator tells me the answer is 7.6923. But remember, I said I was going to round this off after 2 sig figs. That number is above 5. So my final answer will be 7.7%. Let's look at a couple more examples. If I have the percent error for a mass measurement of I want to calculate the percent error, and I measured 17.7 grams, but the correct answer is 21.2 grams. I'm sorry, I just realized I should have said here that with 7.7%, we would consider this to be, yes, this is accurate. Okay, let's look at this one now. The percent error is 17.7 minus 21.2 divided by 21.2 times 100. Now, when I do the subtraction up top, I actually get negative 3.5 according to my calculator, but because of that absolute value symbol, we ignore the negative sign. So I'm just going to scribble that up for now. And I'm going to divide by 21.2 and multiply times 100. Now, notice, and I didn't point it out, I did write down my answer to the subtraction problem with the correct number of significant figures, the correct number of decimal places. But now this number only has 2 sig figs and my bottom number has 3 sig figs. So my final answer needs to have 2 sig figs. So when I do the math, the calculator gives me the answer 16.5094, but I need to round that out off after just 2 sig figs, and so I will have 17% as my percent error. And this is considered inaccurate because it is more than 10% error. Last example, a volume is measured to be 4.26 mils. What is the percent error if the true value is 4.15? Experimental value minus the true value over the true value. Multiply times 100. Let's see, 2 decimal places, 2 decimal places. So my answer needs to have 2 decimal places. So I will have 0.11 divided by 4.15 times 100. Now I don't look at decimal places anymore, I look at number of sig figs. I've got 2 sig figs divided by 3 sig figs. So my answer needs to have 2 sig figs. So my calculator tells me the answer is 2.6506, but I need to round off after 2 significant figures, and I get 2.7%. This is very accurate, well under 10%. This is considered accurate.